So welcome everybody. We're delighted to have everyone here today with us for our webinar, Next Generation Graphics GPU Shader and Compute Libraries. And presenting today will be our Senior FAE, Bob Pickles. So I ask everybody to just make sure that you're on mute because we are recording it, and let's keep any questions until the end. We'll have a few minutes to ask questions. Okay, Bob, it's all yours.
Good day, everyone. I hope you can hear me well. If I'm speaking too fast, then please interrupt and ask me to slow down a little bit. Some of the topics are a little bit complicated, and going against Mary Beth, you might find that you might want to stop me and explain something, so I'm quite happy to do that through the presentation. So I'm known as Bob, but I'm also known as Robert Pickles. So this is the Next Generation Graphics GPU Shader and Compute Libraries, so I'll continue now. It's based on a white paper that I did for Aerospace Tech Week and Embedded World, so that white paper should be available after this webinar. So the agenda of today's webinar is about the history of graphics, graphics libraries involved in the history of graphics, as well as future graphic libraries such as Vulcan, Vulcan SE for certification, Vulcan and CoreAVI. Now CoreAVI we can look at in detail later, and Compute Core, which we found out about before with previous webinars. So a good look at where we are today and how did we actually get here. This is the history of graphics. So the history of graphics started with silicon graphics in the 80s, as well as IBM, HP, Sun, Microsystems, and a few others that were competing for the high-end graphics workstation market. And they all had different graphic library standards, also known as GL. So this was very expensive and very competitive for these companies to make ends meet, and they decided in the end that it's probably best to have one graphics library standard, and they used the Silicon Graphics Iris GL library, which then became OpenGL. So this library became OpenGL around about 1992, but it had a few years to settle down, and when they agreed or ratified the standard of OpenGL. And it wasn't until I think 1994 that Khronos then took it over to make it an open standard. And one other thing that happened in the 80s was the arrival of the IBM PC-80, which had really high resolution graphics of 80 by 20 character displays. But of course, we know today that most PCs have very high-end graphics on them. If you look at your sons or daughters playing games online, you'll see that a PC is probably at its highest displaying games in 4K resolution now. So PCs have come a long way, and they were the death of the other big vendors like Sun Microsystems and SGI because they can compete with the graphics at that level, because the PCs become very cheap in the 90s. So some things have happened since, in fact, 1981 through 1991. I think in the 90s we had the Isobus graphics card, which brought the resolution of PCs up to 640 by 480, which was a massive breakthroughs in the 1990s when we had very, very, very slow computers with no graphics. And of course, we go through to 2020 and we're looking at these AMD and NVIDIA graphics cards that have high resolution GPUs with thousands of cores on board for compute applications. So graphics has not only become a standard for display of graphics, it's also a key technology for compute these days, for high performance compute. And of course, the GPUs of today are no comparison for the GPUs of the past, but the GPUs of today are still using OpenGL. So the basic API goes back to 1991. So you can see that using OpenGL on an AMD or an NVIDIA large-scale GPU is a little bit crazy. So that's why we have other graphic libraries being formed to make use of the technology and move forward into more faster and more efficient graphics. So there's other technology around. We can see Microsoft Direct 3D, Glide Metal Mesa was like a software rendering of graphics, and there's quite a few more graphics technology around, but they'll most likely die out in the next 5 to 10 years. I'll explain why later in this presentation. So the graphic libraries we're going to look at are OpenGL, OpenCL, CUDA, and Vulcan, which is the next generation graphics library. So the key differences between the different graphics libraries are that OpenGL is graphics only. CUDA and OpenCL are only compute-based graphics libraries. So they're not really graphics libraries, but they still use GPU cores to process their data. And of course, Vulkan, the next generation, is graphics and compute. So you can see the issue where all of these are graphics and compute. Everything's moving or merging towards Vulkan, and I'll make this apparent later. So into OpenGL, we can see there's OpenGL and there's also OpenGL SC, which CoreAVI are providing to customers now for primary graphic displays up to a certification level of DAL-A. OpenGL is 100% open source through Khronos.org. So typically, if a company wants to produce any OpenGL derivative, they have to have it confirmed or conformed with Khronos test suites. So we're a member, and CoreAVI are an active member of Khronos. So every GL we release that's safety certifiable has been confirmed and conformed by Khronos. So OpenGL renders into a frame buffer, but it doesn't have any concept of the display hardware, keyboards, mice, and so on. It only knows about rendering into a memory buffer called a frame buffer. So applications mostly run on the host processor to build a frame buffer in host memory, and then it's downloaded to the GPU memory later during the process. So windowing, OpenGL has no concept of windowing, so it uses other display managers such as X Windows, GLX, WGL, and also CGL, as well as EGL. So if you look at most of the libraries from CoreAVI, we need a way of rendering to the display, so we actually use EGL with OpenGL SC. There are other windowing implementations or HMI tools. We're going to talk about those later when we come to certifiable graphics and how to certify HMIs. So OpenGL became very popular because it included bindings for the popular languages such as Java, JavaScript, and C. So it ensured language independence. So the OpenGL library consists of a number of regular objects or data objects, such as a render buffer, different types of buffers, textures, queries, and samplers, as well as container objects, such as frame buffer, which is the end result before display to a display unit. Vertex arrays are holding points or vertices of objects to be displayed. The pipeline, which I'm going to describe later, is the pipeline of sequences that are going to be displayed using the frame buffer and transform feedback, which is another part of OpenGL. It's really more in the future of OpenGL 4, but transform feedback allows the output from vertex shaders to be stored in a transform buffer and then later used to replay those points or primitives on a display. So if we look at the primitives that can be displayed are listed here, but it's probably easy to show what you can do with OpenGL. So it's very basics. So the vertex arrays are actually defining the points in each of these primitives. So that means that the transform feedback process is actually recording these points for later reuse in the display update. So the graphics pipeline, which was mentioned before, has a number of key operations before we get to the actual physical displaying and building of the frame buffer. So the first stage is to take the vertices or points of the primitives and process them through the vertex shader. So basically it takes the points or vertices in the array and creates a primitive shape, which we saw before already, like a triangle or a line, point-to-point line. The next stage is to rasterize the data. That means to physically plot that as a pixel on the display or the frame buffer, but we haven't got there yet because we have to use color depths and color blending to say what color and blend the shape should have before it's displayed. So for example, we might have a triangle defined and the vertex operation is positioned on the display, and then the fragmentation operation might add some shading and colors and so on to make it look like a 3D object, for example, before it's physically displayed or put into the frame buffer. We also have pixel operations, so if you know that you want to write to a specific pixel, you can do that as well using a standard pixel operation. And then the result of all this is to render the shape to a display using EGL or some other HMI tool. So the physical frame buffer is where OpenGL stops. The display of it is where something else takes over and then displays the image. So CUDA. So CUDA has been around since 2007. It's an NVIDIA proprietary technology, and it's used in compute. It's used for artificial intelligence or deep learning, as they say nowadays, as well as high performance compute or computing using the massive parallel processing of the GPU cores. So on a lot of NVIDIA CUDA boards, you find there's normally 1,000 to 2,000 GPU cores available for processing. So NVIDIA defined the term GPU. They were the first to define it, so they know about compute. That was their core business, as well as graphics, of course. So NVIDIA is proprietary, so it only does standards and APIs for NVIDIA hardware. It doesn't do CUDA for an AMD device, a GPU, or imagination device. CUDA will only work with NVIDIA hardware. However, NVIDIA has some really good software development kits as well as GPUs and SoCs, such as the Jetson. So customers are really interested in NVIDIA products, and they do a lot of graphics work with them using OpenGL as well as the CUDA-based compute. So the other thing about NVIDIA is none of the software APIs are written to be safety certifiable. However, some companies will take them as is and use them in low-level safety certifiable systems such as industrial or automotive. And NVIDIA does participate with Khronos because the users of NVIDIA hardware want to use OpenGL. They want to also use OpenCL because they might not just have a GPU, they might have an FPGA or a DSP or some other heterogeneous computer object they want to compute with. And of course, Vulcan. So AMD and NVIDIA are participating with Vulcan for the future graphics and high performance compute applications. So CUDA, how does CUDA work? So it's fairly simple. We have a host computer with a number of cores, and we have everything in the host computer that has to be downloaded or uploaded from the GPU. So the first stage is to download the algorithms from the CPU memory on the host to the GPU memory and the cores on the GPU. The next stage is to load data into the GPU memory. And then the next stage is to instruct the cores to execute and process the data that we've given it. And of course, in the end, is the collection of data from the cores that have processed the data. So this is happening on many, many thousands of GPU cores at the same time that the host processor is running. So the host processor is collecting data and analyzing the results of the GPU core algorithms. So there's no graphics with CUDA, it's only pure compute. And that's typically used on high performance compute and AI systems. So OpenCL is a little bit different because OpenCL has been around since 2000. It was sponsored and defined by Apple, and it was based around the LLVM concept, low-level virtual machine, whereby it's understood that a host processor running on a host has to build or cross-compile algorithms. Can you please mute? Thank you. So LLVM is about cross-compiling algorithms on a host processor to run on a GPU processor. So low-level virtual machine language was used to have a header to define how to compile that object or that C file into an object running on a GPU. And then since then, it's moved on with OpenCL, whereby the standards have been implemented and enhanced to be directly focused on compute, just like CUDA. However, OpenCL is open source, and it also runs on different hardware. So it will run on NVIDIA hardware, it'll run on AMD hardware, Imagination hardware, and so on, as long as they support that interface. So the OpenCL features, we can see it's open source from Khronos Group. That means anyone can write their own OpenCL implementation. But it has to be conformed or confirmed by Khronos. So OpenCL also has some interaction with OpenGL because the code has to be downloaded to the GPU in some way. And typically that's using a compiler which is linked to this LLVM called SPIR. We're going to talk about that later. You can see how that works. So OpenCL was defined for heterogeneous platforms. You can see there CPUs, GPUs, FPGA, which is a special case because FPGAs you can't really change, but you can write pipelines to the FPGA memory to read and write data, because FPGAs are processing data in real time. And also, of course, DSPs and other platforms. There's no graphics, only compute. So the adopters of OpenCL, we can see there, ARM, AMD, Apple, Imagination, NVIDIA. You can see a list of these at this link on Khronos. Could you please mute your microphone? Thank you. So OpenCL works in a very similar way to CUDA. We can see the devices. We can see the host computer, so it has to download the data or algorithms to the compute devices, and it also has to collect the data that's been processed. So the way that this does this is through a standard called standard portable intermediate representation, which means the compiler builds a header file with the object data and the source code to be downloaded to the GPU. Then it cross compiles for the GPU platform, which could also be an FPGA platform or some DSP or some IO device. So it allows different types of devices to be accessed via the host. So it's fairly flexible. So the concepts of a computing unit or device has compute units, which do the processing, and it has processing elements which cover the compute units on that device. So the same implementation with CUDA, you have to download the data to the GPU. You have to cross-compile the software to run on the GPU as well. So everything is the same as CUDA, but it's a more open standard. So Vulkan is the next generation library. So it started around about 2015. And the second release was 2018, so it's fairly new. It's mostly been driven by the gaming industry for fast performance, yet also lower host CPU requirements because most of the processing is done on the GPU. So the commands interact with the GPU, as opposed to the host, whereby OpenGL is building frame buffers on the host mostly. This is doing everything on the GPU, which means the host CPU is freed up, but the GPU is doing more activity. But the GPU has many, many more cores than a host. So we can see some typical games that have been implemented using Vulkan, which were previously using OpenGL, because OpenGL is too slow for the modern games. So the concept of Vulkan was defined as the next gen OpenGL, which tells you that the movement forward from Khronos. So OpenGL has been around since 1991, so it's time for a new standard, a video standard, and a compute standard. So Vulkan is designed to give high efficiency across platforms, access to modern GPUs. That basically means it will run on mobile phones, it will run on laptops, desktop PCs, and other embedded devices. So it should, at the moment, it runs across iOS, Mac OS, Android, Linux, Windows, and so on. And of course, it's fully supported by the main GPU creators. So AMD, NVIDIA, Imagination, ARM, and Intel. Everyone supports Vulkan. And it could replace OpenGL, OpenCL, and CUDA in the future. But that's going to take a few years because there's a lot of CUDA users, a lot of OpenCL users, and definitely a lot of OpenGL users. And to move from OpenGL to Vulkan in one move would take too long from the learning curve. The key thing about Vulkan, as with OpenGL, it wasn't intended for safety critical applications. And it has no concept of high-end RTOS like we know about, for example, Integrity, VxWorks, DOS, and so on, yeah? So we talked about SPIR before. So the new Vulkan has a new standard portable intermediate representation called SPIR-V, SPIR for Vulkan. It's the same concept that all the targets are compiled, cross-compiled for the GPU because there's different types of objects. Then these are encapsulated using standard portable intermediate representation. So it could be a shader, could be a compute algorithm, it could be a special compute shader as well that affects the graphics display output. So some of the objects included that are downloaded using this SPIR-V intermediate representation to the GPU with fragmentation, vertex, geometry, and tessellation shaders. So these shaders may not have been described before, but the vertex shader is a shader that takes the points in a vertex array, the points of the primitives, and it takes them and creates the primitives, as we discussed before. The fragmentation shader might actually take the shape that's been produced by the vertex shader and add color and depth, even 3D type effects to the primitive. Geometry and tessellation are not really necessary, but they can be applied to enhance the primitive's shape in some way. And tessellation shaders basically allow access to different tiles on the display for update. Instead of updating the whole display, they update specific parts of the display to optimize the graphics. As well as this, we have compute algorithms that are being downloaded, and also other type libraries such as compute core algorithms, which we're going to talk about later, that can be used inside the GPU, which will be downloaded and represented using SPIR-V. So shaders are typically created in the high-level shader language, which is interesting for these because you could actually write your own high-level shader and compile it and download it to do a specific job in the GPU. So one thing that's different from commercial Vulkan and Vulcan SC, apart from memory management, so Vulcan SC requires all objects to be compiled on the host, whereas the commercial Vulkan allows on-the-fly compilation and download to the GPU runtime. So that means that if a game is running in a commercial version of Vulkan, it can quickly compile a shader and download it to GPU to do a specific application, yeah? Whereas Vulcan SC, this has to be known about in advance for certification and downloaded at initialization and statically placed. So one thing that is a myth that I've had lots of customers talking about is Vulcan SC does not support OpenCL. There's many customers that assume that OpenCL is supported by Vulcan SC. However, it has been proven that the commercial version of Vulkan has implemented OpenCL for commercial projects to show compatibility with OpenCL, but is not implemented on Vulcan SC, okay? We have to clear that point up. So the Vulkan concept. So VK Core library. So Vulkan is known as VK Core SC, as well as Vulcan SC from Khronos. It provides customer applications access to the VK Core SC library. So they include the VK Core library to access the VK Core SC library. The GPU manager initializes and controls GPU and the display processing unit, which communicates with a KMD, which is the kernel mode driver. So the kernel mode driver is running on an RTOS, for example, and providing direct low-level access to the physical GPU hardware. So the VK Core lib or library and the GPU manager don't physically access the GPU or DPU. The kernel mode driver makes all reads and writes between the GPU hardware. The kernel mode driver may also be a user space driver if requested by customers. So this is an overview. We can see an application with a VK Core library, which interfaces the application to the GPU manager. So it sends its commands and data to the GPU manager, which then is sending data via the KMD kernel mode driver to the GPU and then out to the display. So it's fairly simple. So VK Core will manage multiple GPUs. So there's no single or dual GPU. You could have any number of GPUs in the system and any number of applications using GPU instances to control parts of the GPU. However, for safety certification systems, we have to ensure separation. So the full implementation of Vulkan may not be available for a safety certified system to ensure separation of applications and GPU hardware. So Vulcan SC for safety cert. So Vulcan SC provides support for OpenGL SC1 and SC2. So this is the same API as before for OpenGL SC1 and SC2, but this is actually translating OpenGL SC1 and 2 calls to pure Vulcan SC calls. So these should be a little bit faster than standard OpenGL, but we still have to do some benchmarks on the performance boost. So Vulcan SC also provides virtualization by multi-core access, multi-GPU access, and compositing. So compositing will cover in the next few slides, which is a nice way to combine different frame buffers onto the same display. So Vulkan also has direct access to GPU cores, reduces host processor performance requirements, and reduces CPU temperature, which is very important for longevity and maintenance of the system. Some of the aspects of Vulkan, so it enables technologies such as image edge detect, filtering, blurring, synthetic and augmented graphics. And we can see that in a modern head-up display whereby the pilot can see augmented graphics integrated with the systems on the aircraft to allow him to, instead of looking down at instruments in the cockpit, he can do most of his work with a head-up display. And then we can see radar type missile systems, because one of the things that Vulcan Compute can do is it can replace lower cost FPGA solutions by enabling high performance compute using the GPU cores. So most of the missiles that are in use today, the smaller missiles, are using very small FPGAs like Xilinx 7000. So a GPU costs less than a Xilinx 7000 and it has many more cores and higher performance than a Xilinx 7000, and it might even be a direct fit for Vulkan. So for example, with an i.MX8 processor with Vulkan on top, using the performance of the cores to analyze the transactions required for missiles and missile sensors. So that might be a good fit for missile systems. So one of the other projects we're working on at the moment with Vulcan SC, which has been announced, is the X59 Quest low boom demonstrator. So we can see the design of the aircraft means the pilot cannot see past the front of the nose, but the front of the nose is needed for the quiet supersonic flight. So the way around this is to use a virtual display. That means there's a cockpit display. The pilot can't see outside the cockpit, but there's cameras being used to provide the virtual display. So that means the pilot is flying with a graphics display, so he has no visual sight. So this is certifiable up to DAL-A. We mentioned EASA as well, ED12C. This is FAA DO178. So, oops. Oh, come on. So because the pilot is actually flying in a test prototype system, at the moment this system is going to be certified for DAL-C only. So this is a project that's underway at the moment. It might be interesting for other applications where vision is very difficult. So, compositing architecture. So in a safety cert system, where many applications want to access the same display, we have a system called compositing, which was originally designed for face compliant architectures, whereby graphics applications can draw into frame buffers. The window manager can then access all the frame buffers and display in one go on the display. So what you can do is have a background display that's always fixed. You can have the other displays which can have some transparency and provide objects on top of the main display background. So you can make them transparent so they don't overwrite the background display. And the other items that we can look at as well, because CoreAVI doesn't deal with the display end, it only deals really with the frame buffer end and the libraries like OpenGL and Vulcan. There's other companies such as ANSYS using SCADE Display, ENSCO, IGL, Presagius, and Disti with GL Studio that can use the OpenGL SC to create window systems and even redirect the frame buffers into windows on the display. So it's interesting to note that these companies are maybe a year to a year and a half away from implementing Vulcan, so they can use the VK Core OpenGL SC that we have as a regular OpenGL interface to create displays. The other interesting aspect of Vulcan is it's multi-core enabled already, so that means that the frame buffers could be generated from different cores and merged into the same display using the window manager. Of course, there's only a few vendors that exist for OpenGL and Vulcan at Safety Cert. So this is another interesting requirement from some customers that I've seen already, and it's GPU virtualization again. It could be one GPU, it could be two GPUs. It might be different graphic applications using only one GPU or using both GPUs. So we can see VK Core SC in there with a real-time safety set RTOS. Then we have a video capture module with OpenGL and the compositor, just like the other applications. And we may have to video capture some image from PCI Express using a connected FPGA or another processor card, or even a camera system, which is feeding data via PCI Express or even Ethernet. It depends on the architecture required. So the images might provide, for example, a nighttime infrared flight environment whereby the pilot wants to land the aircraft. And of course, he needs to know at the same time the altitude, the speed, the wind direction, the compass, and other information like the localizer and any other data that may be relevant to him landing the aircraft, such as stall angle and so on. Yeah, these can be captured via PCI using a video capture routine, and they can then use the compositor to add the image, which has no data on top, but just an infrared image, onto the GPU, and the other applications can then augment that image with data. So it also applies to multi-cores, system on chips as well. So if we look at safety certification of graphics, this is what we have to offer for Vulcan SC. So we can see we support a number of different OSs. We support OpenGL SC1, which has been already found to be compliant with Khronos OpenGL SC1 specification. We haven't yet had this done for SC2 yet, so that should be done the end of the year. We could also add in TrueCore. We could also have a Vulcan validation layer, which is probably going to be only used for high levels of safety certification to ensure that the interface from the application is meeting the Vulcan API standard. And of course, we have the safety critical Vulcan driver, we have the video capture unit, and we have encode decode. So this is also supported on i.mxa and AMD E9171 on a wide variety of OSs. So safety certification of graphics, we need to work out how OpenGL users move existing safety cert applications to Vulkan. So we've already seen that CoreAVI are providing OpenGL SC, which is known as VK Core OpenGL SC. So that's a way for existing OpenGL customers to move smoothly to the Vulkan driver and use the API for VK Core SC1, GLSC1. So is Vulkan certifiable in automotive, industrial, trains, and also aerospace platforms? How to achieve that? But it's primarily been driven by hardware because it's a new software library. The types of hardware being supported are basically ComExpress type hardware and also VPX type hardware. So ComExpress or SMARC or ComExpress Type 11, for example, on the i.mx8 form factor, is typically driving the automotive, the transportation, and industrial market. So it has dual GPUs from Vivanti that are safety certifiable up to the highest levels for these markets, as well as aerospace as well. We know one customer, a few customers using i.mx8 as well, certifying to DAL-A on aerospace projects. And the i.mx8 is a little bit different from the E9171 because the i.mx8 is very low power. So the GPUs are much lower power as well and provide much less advanced graphics with far fewer cores for compute applications. Whereas the 9171 is it's got more power, it's got more GPU cores, and it's typically used in military and in civil aerospace, requiring 178 and 254. As it's got more power and it's more flexible and it fits the military type environment of VPX, because typically automotive don't use VPX, they use cheaper varieties of interfaces like ComExpress. So compute core is actually been confused before. It's been Vulkan, but it's not. It's an extension to Vulcan SC, where it's a collection of libraries. So I mentioned missiles. They use FFT computation for missile sensors. Might be interested for missile companies or missile sensor companies who want to implement that on a GPU instead of an FPGA. As well as that, they do other things like matrix manipulation, transpose, optical flow analysis, image filtering, edge detection, blurring, standard, and so on. Yeah, and certifiable to ISO 26262 for automotive, and aerospace standards up to DAL-A. But this is an extension to Vulkan, not the Vulkan driver. It's actually a compute core library that's been defined by CoreAVI, but it should be customized for customers. And that's me finished. Any questions? Anyone there?
You mentioned a lot of
No, thank you, Bob. No question now. I would like to later elaborate on the other application you were discussing. That might be interesting.
The video capture one?
No, about the missiles and stuff.
Oh, yes. Yeah. Okay, cool. Yeah, so in the past, I know that most missiles, I've been to many companies for missiles, they typically use Xilinx 7000 because it's low power. So i.MX8 GPU would be ideal for that application, or the next generation i.MX9.
Well, let's discuss it offline.
Sure, okay. Any other questions?
Maybe I have a question. Because what I was when I was searching regarding the topic, I find out that still the Vulcan compute is not so mature and doesn't have same possibilities like OpenCL. You think it's completely replaceable each other?
Yeah, so I mean, if let me just move back a little bit. So as I mentioned before, we talk about Vulkan and we talk about OpenCL. So we see down here that OpenCL is being used with Vulkan because this standard portable intermediate representation allows OpenCL objects to be downloaded to the GPU. But we don't support it on Vulcan SC, yeah?
Mm-hmm. Okay.
But the reason that Khronos are allowing OpenCL to be used with Vulkan, SPIR-V, is to allow the movement of people using OpenCL to eventually use Vulkan, yeah? Because in the end, OpenCL will be removed, maybe 10 years from now, yeah?
Okay. Because what I find out for now, they aim the Khronos even. They aim the Vulcan compute now more or less just for the computations for graphics still. It's not so like, let's say, OpenCL or CUDA. But maybe they are planning this to be changed in the future. Oh, okay.
Yeah, I mean, the whole point of Vulcan SC is, well, Vulkan is to do compute and to do graphics. So it's to replace OpenGL and to replace CUDA and OpenCL. So Vulkan allows you to download a compute algorithm to a GPU core and run it, yeah?
Yeah. Okay, thank you.
Okay.
I have another question, Robert. You mentioned real-time operating system, but you didn't mention bare metal approach on your slide. Is it possible, and what is the use cases?
Yeah, it's always possible. I mean, we've had a few bare metal projects in the past on typically i.MX6, maybe i.MX8 in the future, just using bare metal with like a GCC library that can be compiled with a very simple scheduler. Yeah, it's possible.
So there is are there limitations when you use bare metal or not?
Not really. Obviously the Vulkan driver would have to be written for bare metal, but typically the Vulkan driver is written for the specific RTOS. So there's nothing to say that you can't write the Vulkan driver for bare metal. That's possible, yeah.
Okay, thank you.
Okay. Any other questions?
Okay, thank you for your question. Some information about the future of POCL project.
Could you repeat the B? Did you say BOCL project?
No, POCL.
POCL.
Yeah. About OpenCL.
Oh, OpenCL.
Yeah, it's POCL. It can use CUDA in Jetson Nano. Like.
Okay.
Yeah.
Yeah, I mean, I've really concentrated on the four main libraries, but it applies. It's on the screen now. So we don't support anything to do with OpenCL or PC. Did you say PUCL? So we don't support any other CL type libraries.
It's a library that use the same interface like OpenCL to to compute in HPC some calculations.
Sure, yeah.
Yeah.
But if they wanted to move to Vulkan, then there may be a way to do that. Yeah, there may be. I mean, there's lots of different teaching exercises on the online for Vulkan, so it's possible to move from any variant of OpenCL to Vulkan for the future. I mean, Vulkan doesn't replace everything now, but as time passes, and maybe 10 years, then standards may then become obsolete, because Vulkan will. If you look at the Khronos website, you'll see there's around about 20 different standards, and OpenGL, OpenCL can be merged into Vulkan in the next 5 to 10 years. And if they do that, it makes it much simpler for the Khronos organization.
Okay, thank you.
Okay. Mickey?
Yeah, many customers are started their GPU with the CUDA, and now when they want to migrate to a certified product, they have a problem.
Correct.
I know that AMD ROC allows you to migrate a CUDA application to OpenCL.
Yeah, but OpenCL is not certifiable.
I know, but the question is whether you're trying to, whether you have some OpenCLs that you support on Vulkan.
No.
Or you have tools to.
So there's two different types of Vulkan. There's the Khronos standard commercial Vulkan that has some tools for OpenCL. And then there's the CoreAVI Vulcan SC that doesn't support OpenCL. But we
yeah.
But the thing is, the API for OpenCL is totally different for Vulkan anyway. So for customers using OpenCL, we could talk to them and try to work out a smoother way to move to Vulcan SC. Yeah.
Yeah, that's what I said. You offered some tools to migrate from OpenCL.
Not at the moment, but it might be possible because Vulkan's been around with CoreAVI for about a year. Yeah, so it's still very new.
Okay.
So if we have OpenCL customers interested, then we can discuss, and maybe some tools will get generated in the future. Yeah.
Okay, I thought it's already around.
Yeah, but not for us. No, not for CoreAVI. We don't support OpenCL.
Yeah, I know you don't support, but you were offering in the presentation. At least I participate. You were thinking of your thought to how you offer. You're planning to offer tools that will allow customers that write their code in OpenCL to move it to.
Yeah, I've seen that presentation already, but that's now been negated. So we don't plan to do that. But we'd still like to talk to customers using OpenCL to discuss ways forward to use Vulcan SC.
Okay.
So and then by talking to customers, we might have some tools at the end of it to convert. Yeah, but not yet.
Okay. Okay.
I saw the same presentation, but it's.
Yeah, but I think that customer already counting on the fact that you will have a tool that will allow them to move from OpenCL to.
Okay, so what I'll do is I'll make a note, Mickey, and maybe we can take it offline, and then we can find out if there is a tool or a tool planned to move OpenCL. Yeah.
Okay.
Okay. Any more questions?
Yeah, actually about that. This is Russell speaking. So your compute core white paper says that it provides facilities to transition to Vulkan compute from OpenCL and CUDA. So maybe that's what Mickey was mentioning.
Yeah,
so do you know what that bullet is about? Or is it the same thing? That's the plan to provide those facilities, or?
Yeah, I think it was a general statement. So right. they could merge to Vulkan from CUDA or OpenCL, but there's still a process of changing APIs and some software development processes, yeah?
Mhm.
But every
Okay.
customer is different, so it would require a meeting, face-to-face meeting, when we're allowed to travel to customers to discuss each requirement, yeah?
Of course.
Any more questions?
No, thank you very much.
Over to you, Mary Beth.
Okay, if there's no more questions for Bob, we'll end it there. Thank you everybody for joining us. Hope you enjoyed the webinar. We've got some more coming next week. We've got compositing and the reuse of software in safety critical graphics applications on Tuesday. And on Thursday, we've got GPU compute and safety certification. So we hope you will join us for that. Okay, have a great day, everyone.
Thank you. Have a great day.
Thank you.
Thank you. Bye.
Okay, bye.
You.